I'm going to present the work that I have done together with my colleagues Emmanuel Agoulot, Abdou Guermouche and Yann Maslia from Bordeaux on QRMAMS. QRMAMS is a solver for sparse systems which has been implemented on top of a runtime engine, well, specifically the StarPU runtime engine. So here we're interested in solving linear systems with a matrix A which is rectangular, potentially large, and sparse. And so, of course, we want to take advantage of sparsity for a number of reasons that we all know. And the method that we are using for doing this is the so-called Multifrontal QR method, which is guided by, which basically computes the QR factorization of a sparse matrix, okay? So it's a direct method. And it is guided by a graph which has the shape of a tree, which is called the elimination tree, where each node of this tree is associated with a relatively small dense matrix, which we call a front or a frontal matrix. And this tree is processed bottom up. And when a node is visited, we do basically two operations. One which we call the assembly operation, where we allocate this frontal matrix and we fill it up with coefficients coming from child nodes. Okay, so we take coefficients here and we assemble them into the parent. And then once the node has been assembled, we factorize it using a dense QR factorization, like, for example, what you can find in LAPACK, okay? And we have two sources of concurrency here, one which we call tree-level concurrency because nodes that belong to different branches are independent and thus they can be treated in parallel, so at the same time. And we also have a node-level parallelism coming from the fact that these frontal matrices can be quite large, and then we can use multiple processes to treat each one of them. In practice, this elimination tree can have as many as 100,000 nodes, and frontal matrices can be as small as 2 by 2 and as big as 100,000 by 100,000. Okay, so this is a very large, heterogeneous, and irregular workload. Okay. Now we are in this context here. We have a complex application, which is our multifrontal QR method, and we want to implement it on a complex system which may be made of multiple nodes with multi-cores, GPUs, whatever you like. Okay. Now the classical approach to doing this is by mixing a number of technologies, MPI plus OpenMP plus CUDA. Okay, and we've been doing this for many years now, and it works okay, but it may lead, it requires a big programming effort, and then it may lead to code which is difficult to maintain and update, and which is prone to portability and performance portability issues. Okay, so we want to use a different approach, which is based on the use of a runtime system, which can be seen as a layer which makes an abstraction of the underlying machine and provides the programmer with a unified programming model, okay, which is supposed to be portable across a wide range of architectures. And among all the runtime systems that are available today, we are interested in those where the workload is expressed in the form of a graph of tasks, a directed acyclic graph of tasks. And now this can be expressed using different programming models. And among all the different programming models that exist today, we have chosen to use one which is called sequential task flow, which is very simple. So basically, instead of executing operations, you submit tasks. But when you submit a task, you also tell the runtime how the task accesses the data, whether in read or write mode. And then the runtime, just by looking at the order in which tasks are submitted and at the way they access data, it can automatically detect dependencies among them and build automatically the DAG and then deploy it on the underlying machine. So take, for example, this small code here, which is made of 4 function calls, A, B, C, D, which access data X and Y in different ways, okay? Read or write mode. Now, the corresponding sequential task flow code, we would first submit a task for subroutine A, and we would tell the runtime that this task accesses data X and Y in read-write mode. Now, when we submit a task for subroutine B, we tell the runtime that this subroutine accesses data X in read mode, and now the runtime sees that this task needs data X, which is updated by this previously submitted task, and then that basically means that there is a dependency between them, which is represented by this edge. And then we do the same for task C, and task D, and so we would end up with this graph of tasks, and you can easily see that if we have more than one core, tasks B and C will be executed at the same time because they are independent, okay? There is no edge going from B to C or the other way around. Now, submission of task is asynchronous, so that basically means that when you submit a task, control is immediately returned. Therefore, if you want to make sure that all the tasks are completed, you have to put a barrier somewhere, okay? This is actually a very nice thing. You know, if you can just avoid it, you can have extra speed up. And then one nice thing about modern runtime systems is that they can handle data. So for example, if task A is executed on CPU and task B is executed on GPU, the runtime will move data X from the CPU memory to the GPU memory automatically. So we don't have to do anything about it. It's the runtime who moves the data from one side to the other. And actually, it can do all sorts of smart tricks, like, for example, prefetch the data, or, I don't know, have multiple copies of the same data in order to minimize the impact of communications. All right, there are a number of runtimes that comply to this programming model. For example, OpenMP is one of them. But we have decided to use the StarPU runtime because it has a very, very wide set of features, and we will see some of them. All right, so how do we implement our multifrontal QR method on top of StarPU? So here on the left, you see a very tiny elimination tree where we have supposed that frontal matrices are partitioned into block columns, okay? So a 1D partitioning. And what you see here on the right is a very simple sequential code that achieves the multifrontal QR factorization. So this is a loop over all the nodes in the elimination tree. When a loop is visited, memory is allocated, then it is assembled, so it is this doubly nested loop here, and then it is factorized, so this is a dense LAPACK factorization block column by block column, okay? Now the corresponding sequential task flow code looks like this. So basically we just replace function calls with summation of tasks. And now we have a sequential code that runs in parallel, okay? So very simple conceptually. And this basically allows for transforming the elimination tree into a DAG of tasks, which looks pretty much like this, where basically tree and node parallelism are expressed in a very consistent way, okay? And actually we can go even a little bit further because we can start working on some tasks associated with the top node before all the tasks associated with the children are finished. So we have an extra concurrency which we call inter-level concurrency, okay? All right, so actually in practice what we do is we do not really use a 1D block column partitioning like this because frontal matrices are commonly very overdetermined, okay? They have many more rows than columns. So you understand easily that it's not a good idea to, you know, cut a sausage in, you know, along its length. So this simply does not deliver enough performance. So actually what we use is a 2D decomposition into blocks or tiles if you wish. And then we use communication avoiding algorithms, QR factorization algorithms for factorizing each frontal matrix, okay? So what do we expect from this? Much more concurrency than in the 1D case, but also a much larger DAG with many more and more complex dependencies, many more tasks, and tasks of much finer granularity because we have decomposed data into smaller blocks. So the question is the runtime capable of handling all this added complexity? But what is important is that even if we have a much more complex method, which is much more difficult to parallelize, we just have to write a sequential code because parallelization is taken care of by StarPU, okay? Conceptually, so practice is a bit more complicated than this, but you know, conceptually is as easy as this. So results, we have taken a few matrices from the suite sparse collection. Here they are sorted in increasing complexity. So topmost is the smallest one, and the bottommost is the largest one. And we have run this code on a 32 cores machine. So we only do shared memory. We can only handle shared memory systems at this moment. All right. So speedups. Gray is the version with 1D decomposition into block columns, and green is the 2D decomposition. Okay. In the 1D case, what you can see is that sometimes speedups are not that bad, okay, almost 25 out of 32. And in some other cases, speedup is quite poor. And this happens for the smallest matrices, because the 1D simply does not deliver enough concurrency. And for this matrix here, which is quite large, but actually, if we look at its elimination tree, we would see that it contains extremely overdetermined matrices, frontal matrices, okay? For example, there are frontal matrices with millions of rows and only a few thousand columns, okay? So clearly 1D partitioning is not good. With 2D partitioning, instead, we have pretty much the same speed up regardless of the size and the shape of the matrix, which is a very desirable property for a black box solver. And then overall, we have almost a speed up of 25 out of 32, which is not bad at all. Question is, why don't we get 32 out of 32? Okay, so we have identified 4 possible sources of inefficiency which we measure with 4 efficiency measures. One which we call the granularity efficiency. So what is this? When you run sequentially, you don't have to partition your data, okay? Because you don't care about parallelism. So when you want to execute, for example, your blast operations, you want to do them on data which is as large as possible. But when you are in parallel, so you have to partition your data and partition your operations. So that basically means that your blast calls will be of smaller granularity, which implies a loss of performance. Now, task efficiency. Imagine that you have 10 tasks, all independent, okay? And you execute them sequentially, one after the other, on the same CPU, which is close to the data the tasks work on. So you get a certain execution time. And now you execute these 10 tasks all at the same time on 10 different cores, okay? The time for executing each task will be a little bit higher because there's contention on memory, because there are remote data accesses, for example, in a NUMA system. And this we measure with what we call the task efficiency. And pipeline efficiency, so ideally we would like to have a DAG with no edges. So that basically means that all the tasks are independent, but life is not that easy. We have dependencies, and this basically means that maybe at some point, even if we have like 1 billion tasks left to be done, none of them is ready. So CPUs will have to wait for some tasks to become available, okay? And this implies stalls, idle time, which make performance a little bit worse. And finally, runtime efficiency, which basically measures the overhead of the runtime engine, okay? The product of all these efficiency measures here gives the efficiency, the global parallel efficiency of the code. And actually, a couple of days ago, I stumbled upon the web page of this project, which is represented here by Brian, and I've found something that really looks pretty much like this. So this is basically something that we have to discuss about maybe later before we start drinking wine. Okay, so this is what we have measured on our code. So again, gray is the 1D decomposition, color is the 2D decomposition. By the way, all these measures, we did this like a couple of years ago and we had to do it by hand, but now it has been implemented inside StarPU. So basically, if you push a button, StarPU will provide all these statistics for you automatically, okay? And this is another advantage of using a runtime system, because the runtime has full control of your code and of the system that it is running on. So this is definitely a favorable feature of runtime systems. So granularity efficiency, not surprisingly, it is better for the 1D case than for the 2D case, simply because in the 2D case we have decomposed data into smaller pieces, okay? So granularity efficiency will be worse. Task efficiency, instead, it is better for the 2D case because these smaller blocks are more cache friendly, okay? So if you have a scheduling policy which is, cache aware, which we do, you can get better task efficiency with a 2D decomposition than with a 1D decomposition. Now, pipeline efficiency. So as we said earlier, the 1D decomposition does not deliver enough concurrency for small problems and for this problem here. And this is what we actually see, okay? Pipeline efficiency is pretty bad here and here. With the 2D case, instead, we have pretty much the same pipeline efficiency for all problems. And finally, runtime efficiency, this is always above 98%, so that basically means that the overhead of the runtime is negligible, okay? And so we've done the same analysis for machines with GPUs, but it's a bit more complicated. Now this is scalability on a power rate machine to 20 cores for a number of problems. And what you can see is that for the largest problem, we have a pretty impressive parallel efficiency of 88%. So that basically means a speed up of 17.6 out of 20. Okay, so this is quite impressive. And then KNL, so I'm not going into the details because we've already seen this morning. What we have seen is that our code is very sensitive to configurations of the machine, of course, and also of the software environment. Okay, so hardware-wise, we decided to configure our machine with a quadrant and cache configuration. Although we are, simply because our data does not fit into the fast memory. Okay, so it's much larger than that. So we have to think about smart ways of handling the fast memory when in flat mode. And software, so there are a number of tricks that you can do to speed up your code. And so this is actually what happens when we use some of these tricks on a number of problems here. So the orange bars are the base version. So this is the same setting that you would use on an Haswell machine, say. So nothing special. But then, for example, we use what is called like a smart memory allocator from the Intel TBB scalable allocator from the Intel TBB library. So this gives a little benefit. We activate transparent huge pages, and we get the yellow bar. Then we use both TBB allocator and transparent huge pages, and we get the green bar. And then we use explicit huge pages and TBB allocator, and we get the red bar. And then when we do all of these tricks, we get the dark blue bar. And actually, you can see that the difference can be quite important, right? So this is scalability on a KNL from 54 to 64 cores. Okay, so this is the very end of the big curve that starts at 1. What you can see is that at every step there is an improvement. So that basically means that the code scales. Okay, so which is good. And the numbers that you see here on the right is the parallel efficiency, which is measured like this. This is the measured speed up divided by the ideal speed up, okay, which is clearly 64 divided by 54. What you can see is that in some cases, in most of the cases, we are above 90%, which is a good result. Quick resume. So this is CPU only code. We have 6 configurations. So the 20 cores Power 8, 32 cores Sandy Bridge, 24 cores Haswell, 36 core Broadwell, and then 2 KNLs, 64, 68 cores. And what you can see is that, so this is always the same problem, okay? So this is kind of the ideal matrix. What you can see is that on the 2 KNL, actually, we passed the teraflop mark, which is quite impressive for a sparse code, okay? On a single node. All right, GPUs. So I don't have to convince you that GPUs are good, are green, are fast, blah, blah, blah. We're not just interested in using GPUs, okay? So we want to use all the resources that are on the machine. So GPUs and CPUs at the same time, okay? But this poses a number of problems. First problem is granularity, because as you might know, GPUs are happy when you give them big chunks of data to work on, okay? So if you give them like small operations, they will not get good performance. But this is very different from regular CPUs, because CPUs reach asymptotic performance on much smaller data, okay? And then we have a scheduling problem, because now we have units which have very different speeds and very different capabilities. So we have to decide who does what, okay? And then we have communications, because we have to move data from CPU memory to GPU memory and the other way around. And of course, we don't want to, pay the cost of these communications. All right. So how did we tackle all these issues? So granularity. The code that we have seen before, the data, the frontal matrices were uniformly decomposed into small pieces. Okay, and this is because we have many CPUs, and we want to feed all of them. Okay, this is not good for GPUs, because GPUs want big operations. The other way around, we could partition frontal matrices into large pieces. Okay, so GPUs would be happy, but we would not have enough tasks to feed CPUs and GPUs. Okay, so this is not a good choice. So there is a compromise to be found here, and the way we decided to get this compromise is to use a hierarchical dynamic partitioning scheme, where frontal matrices are first decomposed into big chunks. Okay, so we have big chunks which are updated using large granularity tasks. But then when one of these chunks has to be factorized, it is dynamically redecomposed into data, into pieces of small size. So basically what we have is a mixture of small tasks and large tasks, which we can use to to feed all the working units. And how do we do this in practice? We just insert in our data flow partitioning and non-partitioning tasks. Okay, so we have regular tasks. We just partition and unpartition the data. And the nice thing is that StarPU takes care of coherency between the data. Okay, so coherency between, for example, a large block and all the small pieces it is decomposed into. All right, scheduling. So we have basically seen that our DAGs are very regular. They can alternate regions with lots of concurrency, with regions that have very little concurrency. Okay, so we don't want to use the same scheduling policy in these two cases. So we decided to implement our own scheduling policy, because in StarPU you can do that. Okay, there is an API for implementing your own scheduling. And so our scheduler actually is capable of switching automatically between two states, one which we call the steady state and one which we call the critical state. So in the steady state, we have lots of concurrency, we have lots of tasks, okay? So we know that we can feed all the processing units, so what we want to do is give a task to the unit which can execute it fastest, okay? So we want to have the best matching between a task and a processing unit. In the critical state instead, we don't care about the best matching between task and units, but all that we want to do is go as fast as possible through the critical state. So we want to go as fast as possible from here to here, okay? So what we basically do is we give higher priority to the tasks which lie along the critical path. In both cases, we can do prefetching. So basically, we can anticipate a little bit the assignment of a task. So we know a little bit in advance where a task will be executed, so that when the execution of the task actually starts, the data is already, on place. Okay? So actually, we don't pay the price, or much less the price of data transfers between CPUs and GPUs. All right. So results. So this is a test, the first test with a GPU-only code. So here we decompose the data uniformly into big chunks. Okay, so we know that this is good for GPUs, but not for CPUs. So we run this code only on GPU. Okay. Now this is the CPU-only code. So again, uniform decomposition into small pieces. Okay, so small granularity. And now this is 12 cores plus one NVIDIA K40 with the hybrid, hierarchical dynamic partitioning and the smart scheduling that we have seen on the previous slide. So as you can see, we get a nice speed up here. And then this is again CPU only code, but with 24 cores now, and 24 cores plus one NVIDIA K40. So basically what you see is that when we add some resources, be it CPU or GPU, we get a speed up. So that basically means that QR mums can take advantage of all the resources that are on the machine. All right, so this is, with the gray background is the same that we have seen before. So this is CPU only. And now this is performance on a 24 cores as well, with 1 K40, 2 K40, 3 and 4 K40. And for the last result, actually, we hit the 3 teraflop mark, which is quite good. All right, other features. So we have implemented a feature that allows us to tell QR mums, you can use this many cores, but you're not allowed to use more memory than this. Okay, and QR mums will go as fast as possible within that imposed memory envelope. Okay, so this is the memory consumption for a sequential test. Okay, so this is time, and as you can see, it is very variable because frontal matrices are allocated, and they are allocated as we go up the tree. Eventually, it reaches a maximum here, which we call the sequential peak. This is a parallel execution with 6 threads. Okay, so as you can see, time is divided by almost 6. But memory consumption, spikes, goes very high. And then this is the case where we tell QR mums, okay, so you can use 6 threads, but don't use more than twice this sequential peak. And as you can see, so QR mums will be nice and not violate this constraint. And as you can see, the execution time is barely affected. Okay, so there's just 0.1% more execution time. And then there are a number of other features, like for example, as I said, submission of tasks is asynchronous, so that basically means that I can submit tasks for the factorization of 3 matrices, And the 3 factorizations will be pipelined, okay? So the second factorization starts before the first one is finished, okay? And then, performance analysis. Oh, another nice thing that we have, SimGrid is a simulation engine which can be plugged inside StarPU. So by doing this, we can simulate the execution of QR mumps. So that basically means that on your laptop, you can simulate the execution of a code on a KNL, okay? Without paying the price of buying a KNL. And simulation is pretty accurate, actually. I think I'm done. Just a few advertisements. So all this is done in the context of this project, which is called SOLHAR, which is an ANR project in collaboration between Toulouse, Bordeaux, and Lyon. So SOLHAR means, okay, solvers for heterogeneous architectures using runtimes. And if you're interested, you can just go hit this link here. And if you want to factorize matrices, you can download QR mumps at this website. Thank you.